Hey, what's up, guys? Just a disclaimer. If you don't know about uh, if you don't know about union find, I was going to say union sets. I was like, what is that? If you don't know about union find or disjoint sets, please look them up. You won't really understand the solution or how to approach the problem unless you really understand those first. Also, guys, just to mention, the way I approach these problems is if you just want the solution, you can skip a forward, probably till the end of the video, and I walk through the solution. I explain that at the end. But the way I kind of want to do these LeetCode videos is help you guys understand the intuition behind getting to the algorithm, getting to the optimal algorithm, getting to the solution, like understanding. Oh, why is it like this? Oh, how do I get from here to here to here to here to the final solution? So that's why I spend a lot of time explaining it, trying to explain my thought process, so it benefits you guys and also benefits me in helping me explain that. So if you just want to focus more on understanding the solution, getting the answer, you can skip forward, and that's where I'll do the solution walkthrough. But the first half is usually just me kind of explaining the problem, how to approach it, why it's like this, why it's like that, and helping improve your intuition and my intuition. Hey, what's up, guys? Today we're doing problem number 1579. Remove max number of edges to keep graph fully traversable. Before I begin, don't forget to like, subscribe, and check out my other content. I make a lot. I'm planning on doing tech tutorials. I do book reviews and vlogs and just a bunch of other stuff. So check out my channel if you have the time. Okay, so Alice and Bob have an undirected graph of n nodes and three types of edges. We have a type 1 edge, a type 2 edge, and type 3 edge. Type 1 means Alice can go on that edge. Type 2, only Bob. Type 3, both of them can use that edge. Okay, so we have an array of edges where edges I is equal to type U, V. Okay, so each edge has the starting node, ending node, and the type, whether it's type 1, type 2, or type 3. Okay, I'm not going to read the whole problem because if you're here already, you probably read the whole problem. So find the maximum number of edges. We can remove after removing the edges, so we want to be able to keep removing as many edges as we can, right? So that both Alice and Bob can still visit every node in the graph, okay? So we want to return the maximum number of edges you can remove, or return -1 if it's impossible for the graph to be fully traversed by Alice and Bob. So return the maximum number of edges that we can remove such that both Bob and Alice can still traverse the entire graph from one node. Okay, great. So we have this example 1, 2, 3, 4. Red is type 1, green is type 2, blue is type 3. We have this list of edges. We have 4. The output is 2 because why? If we remove the two edges 1, 1, 2, which is from 1 to 2, and remove type 1, which is the red one, and then remove 1, 1, 1, 3, so remove this edge. So remove this this red edge and this red edge, then both of them can still traverse the graph because blue means they both of them can use it. So 1 and 2, both Alice and Bob can visit. 2 and 3, both Alice and Bob can visit next. And from yeah, so from here, Bob can come. Or was it Alice? Yeah, from 3, Bob can reach, and from 2, Alice can reach to 4. So they can all visit 1, 2, and 3, 1, 2, 3, and 4 if we remove those red edges right here. Okay. And how are we going to approach this problem? Well, remember what I said in a couple of videos earlier that before I explain it, what you want to think sometimes if you're stuck at a problem is we know that we have this edges and you want to slowly remove the edges, right? You can think of it like that. Or you can always approach the problem backwards, okay? You can always approach a problem backwards, and that might make things easier. Why am I saying that? What's the backwards approach here first? So the backwards approach here is instead of removing the edges, why don't we build the graph such that both Bob and Alice can visit all the nodes while pulling from the edges. So instead of having this list of edges and removing from it, well, instead what we can do is have an empty list of edges and start taking edges and kind of build our graph that way. Why am I saying that? Because if we were to remove the edges, it would be a little more complicated. We have this list of edges. We'd have to remove one, check if everyone can visit, remove one, check if everyone can visit. We can probably change it up a little bit, but that's definitely a more complicated approach than just starting with an empty set of edges and slowly building our graph out. Okay, so we know we want to do that. So we know now that we have this list of edges and we want to slowly build up our graph. Okay, so now how are we going to build the graph? Well, we need to start pulling the edges in. So what edges can we use first? What are the best edges to start using first? Well, they're the type 3 edges because both Bob and Alice can use them, right? So we want to make sure we use all our type 3 edges first and then use type 1 and 2. So the first thing we're going to have to do is sort our list of edges. and then we start iterating over them. So we start visiting type 3 edges first. That's number 1. Okay, so let's just write that down here. Sort edges, so we visit type 3 edges first. Okay, that's number 1. Now, what we're going to do now is we're going to okay, so now what we're going to do is we're going to maintain kind of 2 separate graphs, okay? Maintain 2 separate graphs. One graph is that which Alice can visit, and the other is Bob's graph, okay? Now, each graph is going to start off with just a set of nodes, or instead of thinking of them as nodes, we can think of them as unconnected or disconnected. That's the word. Disconnected components. Okay. So each node individually is a set of disconnected components. Okay. So we have Alice's graph and Bob's graph, and now each of them have their own. Originally are a disconnected set of components. Over here, just nodes, and over here, just nodes. And all we need to do is that we need to visit each edge. Okay, we have this set of components, this set of components, this set of nodes, this set of nodes. And now as we visit each edge, we need to start connecting them. Okay, we need to start building out Alice's graph from the edges, and we need to start building out Bob's graph from the edges. Slowly start connecting these nodes together. Okay, so we iterate through the edges, and we slowly build up the graph. And we slowly connect the components together. Okay, so we're gonna go through the edges, and we're gonna connect Alice's components, and we're gonna connect Bob's components. Okay, now as we're connecting the components, we need to check. Each edge has a starting node and an end node, or basically each edge has 2 nodes. Now, every time we visit an edge and we visit those 2 nodes, those nodes might already be part of a component. Those nodes might already be a part of a component. Okay? So let's just give an example. We're going through Alice's graph right now. We have 2 nodes, and now node A is part of one separate component already. Node B is a part of another component. Maybe because of a previous edge, they were attached to another component. Okay? So we're building out 2 components. Just imagine that. I don't use diagrams. To be honest, it's a lot of work for me. But yeah, so we have 2 separate components. Maybe in the future I'll start using diagrams, but for now I want to just stick to this and then do those later after I get consistent with this. So we have these 2 separate components. And now node A might already be part of one component, node B might already be part of another component, simply because from a previous edge, they were already connected, okay? But now node A and node B aren't connected to each other yet, okay? Their components aren't connected to each other yet. How will we know their components are connected to each other yet? We'll talk about that later. We're gonna use something called union find. And if you don't know what union find is, I highly suggest you pause right here, go watch some videos on union find, go watch some videos on disjoint sets and figure those out, and then come back here, because you won't really understand the solution until you know that. Okay, so we do that, we split them up, and then we want to connect those components. So we have node A is part of one component, node B is part of a component, and now we want to connect those components, because now this edge can either connect this component. Now, what if node A and node B are already part of the same component? That means this new edge is redundant. Okay, let's write that down. I know it's a lot, but let's just kind of make this sense now. So we iterate through edge. Okay, now when we hit some edge, we want to check, is node A of that edge part of the same component as node B? If they're not, that means node A is part of its own component, node B is its own component if they haven't been connected yet. I mean, the first time we saw node A and node B. Anyway, so are they part of the same component? If same, then we can ignore this edge. Else, then we need this edge, and we'll connect them. And we'll make node A and node B part of one big component, and that means every other node that's part of component, every other node that's part of the component that node A is in. Basically, every other node that's part of node A's component will also be connected to all the nodes in node B. So basically, we're putting those two components together through this edge. And that's our general solution, okay? And you'll understand that a lot better once we get to the code, but this is basically how we're going to approach this problem. We're going to go through the edges. We're going to have we're going to have Alice's component, Bob's components, and as we go through the edges, we're going to start connecting the components together. If at an edge, both the nodes at the edge are already connected, that means we don't need this edge to connect the two components, and we can just get rid of that edge. Okay? That means we can just get rid of that edge, and we can keep moving forward. So that's that. So now let's go through the solution. I have it right down here. Okay. Now this is going to make a lot more sense once we start looking at the solution. So I created some constants, so it makes a lot more sense. So Alice's edge is type 1, right? Bob's edge is type 2. Both edges are type 3. Okay, so first thing we do is sort the edges because we want to hit type 3 edges first. And now we're going to maintain, we're going to use a union find. Once again, if you don't know union find, the string tense, please search that up. But anyways, so these are Alice's set of components or Alice's roots, and Bob's set of components or Bob's roots, meaning the roots for each of the components, okay? Then first thing we do is set the roots for each of them to themselves. This is how we'll know that we're at the end of a component. Then we keep track of how many components Alice has, how many components does Bob have. They're both equal to n, and this is our answer. Then we go through all the edges, and this is how it's going to work. So first thing, now these are going to be the first types that we see, which is the both edge, which is type 3, right? If the edge we see is of type 3, that means both of them can visit. And so now what do we do? So now we find, basically, this is node A, right? Since both of them can visit, we need to find node A, Alice's, we need to see if it's in Alice's components and Bob's. I'll explain what I mean in a second. Anyways, so we have node A and node B, remember, because each has two nodes. So for node A, right, we want to check what's the, so for node A's component, we want to check the roots. And from node B's component, we want to check the root in Alice's graph. Basically, if they have the same root, that means they're part of the same graph. They're part of the same component. If they have the same root, that means they're part of the same component. So now we check this component and this component, and then we also do that for Bob. For Bob's graph, we check A's component and B's component, and then we check. So if Alice's component and if Alice's node A and node B are part of different components, that means we need to connect them to make the same component. So what I do is I set one root to the root of one to the root of the other, and that means they're basically connected. Okay? And then I subtract the number of components Alice has because now we just got rid of one, and because we combined two into one. And we do the same thing for Bob. If Bob's two components are different, then let's connect them and subtract one for both counts. Otherwise, if both Alice's two components are node A and node B are the same, meaning the components are already connected, and so is the same for Bob, that means we don't need this edge, and we add one to our answer, meaning we can get rid of this edge. So if Alice's components are the same and Bob's are the same, that means we don't need this edge. Then, so this is the case when we hit a type 3 edge. Okay? Now what if we hit a type 2 edge or a type 1 edge? Same thing. Okay, it's a little different, but now we don't need to check for Bob and Alice since only one of them can visit. So if it's an Alice type of edge, we'll make the roots for Alice. We're looking at Alice's set of components now, or Alice's graph, and same thing for Bob. If it's Bob's edge, meaning if it's not Alice's edge, then we'll check it for Bob. And now basically what we do is we find node A's component and node's B component, meaning we find the roots of their components. If the roots are the same, once again, that means they're part of the same component. If they're different, that means they're part of different components. So if they're part of the same component already, that means we don't need this edge, and we can increment one to our answer because that's another edge that we removed. Else, if they're different, then we connect them by setting the root of one to the next. Once again, please look up unions and disjoint sets. I don't want to spend time explaining this right now because it's a long, complicated topic. Now, once again, Then we want to decrement one of their counts. If it's a Alice edge we're looking at, we decrement Alice's number of components since we connected two, and now we just made them into one. Else we just decrement from Bob's. And we keep doing that. What find does, it basically finds the root. This is a simple union find method, or destroying set find method. And at the end, if Alice's components aren't one and Bob's component aren't one, that means we return -1. That means they aren't connected. They weren't connected to begin with. Okay, they weren't connected to begin with. The edges that we hadn't connected the graph yet, and it fully connected the graph yet. So if they're not -1 and not -1, then we, not 1 and not 1, then we return -1. Else we just return the answer. That's basically it. I hope you guys enjoyed. Like, subscribe, comment. I know this explanation in the beginning was a little bad, but it's a little hard to explain without seeing the code and without knowing what disjoint sets and unions are, and I didn't want to rely on that as I was explaining in the beginning. So, yep.